Hello, hello. I'm super happy to see so many faces. I think it's one of the very few talks that doesn't have Java, JVM, or even like letter J in the title. So, but we are going to talk about a very, I think, interesting topic. So for the next 45 minutes, we'll explain you how Google works. Also, you may want to ask questions. We'll take questions at the end, so you can go to the Slido, there's a QR code, and don't be afraid to throw the hardest questions. So my name is Monika. I'm engineering manager based in Google Warsaw, working on internal infrastructure, internal storage. And there's also Sławek and Janek with me. They're senior engineers in my team. And as I said, we would like to do a brief introduction about the storage, but also do a little deep dive and explain some problems that are challenges in our daily work. So let me talk about storage in general. So why we even are talking about storage. So at Google, we have very uniform software stack and technology stack for any service that we are building. And all Google services are based on, I would say, these three pillars, these three main services. The first one is Colossus. So Colossus is the next generation of something that you may know as GFS, so Google File System. So it's a distributed file system that we have at Google. There's also Spanner. So Spanner is our relational database that we use across Google. So if you happen to use GCP, Google Cloud Platform, you surely might have encountered the flavor of that, which is Cloud Spanner. And finally, we have Borg. So Borg is our cluster management service, a job scheduler. If you know Kubernetes, it's something very, very similar. So in fact, Kubernetes was built based on some learnings of Borg. So with these three services, there are some main building blocks to build all the storage solutions that we have at Google and are available for you. So like both in-memory storage, but also databases like relational databases, NoSQL database, BigQuery also uses all these three services. And finally, GCS, so like a storage for unstructured data. All these services are using Colossus, Spanner, and Borg. Moreover, GCP is pretty new to Google, in a sense that before GCP, there was also need for these services and this functionality. So YouTube, Gmail, Photos, like any service that you can imagine that exists at Google also is built on these three main services. So how it looks. So if you think about storage, bottom up, first you have some disks, some hard drives, and some software layer above that. So we can do some health checks to see if hard drives really work. And then there are clusters. So cluster is something that you may see on this picture. So it's a set of racks interconnected with very, very dense network with very high throughput and low latency. And what should be taken into account that disks fail. And by disk fail, I mean that they fail on daily basis. So based on our learnings at Google in data centers, and on average, 2% of disks failed every year. However, we can see even spikes to 10% of disks, which means that this infrastructure is never fully available, and just we need to take into account that data will disappear because we lost some data due to disk failures. And finally, what is the most interesting for you, it's that we divide the storage into zones, regions, or global offerings. So for instance, if you use GCS, you can select whether you would like this file to be available in a zone, in a region, or maybe you would like to have this file available globally. So the next thing, that was I would say bottom up, but from the developer perspective, you don't really want to care much about what's happening under the hood. So for like your success, important is developer velocity. You want to deliver fast. So you don't want to deal with all the details. And also you have some expectations regarding like latency, durability of data, and you just want to be there. But from our perspective, there are many challenges. So first one, like the data access patterns can be very different. So we support many users, as I said, like we have these internal users, we have GCP users, we have users that run very large workloads. So they access a lot of data, but they're not really latency sensitive. Whereas you, if you provide a service for end user and you need online access, you would like to get this data in like milliseconds. So you also would like to see a uniform access. So you don't need to really care what this data is like locally on the disk, in the same cluster, in the same zone or region. And also you don't have to worry that much how much data you read and like for what's the purpose. You also expect uniformity of performance. So again, like you really need something to like ensure that regardless of data placement, like you can have the same functional and non-functional properties of your data. So you have like high availability, you have durability, of course, because it's storage, and also relatively low latency for your workloads. And finally, you'd like to have some monitoring. So we'd like to have an insight on how the storage operates, but you really don't want to like go like lower than that. So the question is how we build a distributed file system that supports all the different workloads and use cases. So this is something that Janek will tell us about.
Thanks, Monika. Thank you. So I would like to start presentation with our file system that's called Colossus. It's the next generation, next iteration of the Google file system you might have heard about or you might have read about it. And this is actually something that drives the whole of Google, and not only Google, but it also drives the Google Cloud Platform. As already said, like we have the same storage for everyone, and you might heard the joke that the cloud is just someone else's computer. But actually, we don't give you the computer. We give you the service that runs on the hardware, and that service is defined in software. So Google is very strong on software-defined everything. Like we are the pioneers of software-defined network, and we are also pioneers of software-defined storage, and that is, I think, quite important. All right, so let's dive in. We'll start like assuming that Google Cloud Storage system is using this, and we will go through like the life of the data as seen by the GCS service. So the GCS service is using the Colossus client library, which is the entry point into the storage, and this library has an API that lets you express your wishes against the storage. So like what kind of shape of the storage you would like, and how resilient you would like the storage to be, like how do you want to make your data shaped to protect you against the inevitable storage failures, and how you want to have the data laid out, etc. That client library interacts with our control plane, which is called Colossus Curators. And this is the key point to scaling, and also key difference to Google file system, which was not as scalable as we would wish it to. And this is also the blueprint on which all storage services build. So Colossus Curators are answering the calls of the clients, and there's like if you interact with the system and you ask about data, so you ask about the metadata, so data on data, you would be interacting only with curators, but then the curators would know nothing about the actual data flow, because that would be offloaded to a separate channel. So curators will just serve very small amount of traffic, which is just the traffic about the data. So they they are not impacted by the large amounts of data that is being stored. So curators are like shared nothing architecture, and also they don't hold data. The data is stored in the scalable Colossus metadata database, which is big data. Like this could be no SQL database shard by key, and it happens to be a big table. There is a lot of clever engineering allowing to do that, because Bigtable, of course, stores its data on Colossus, because where else, right? So that is a bit tricky, but we can, and we do make it work. Then there is actual data storage, and data storage, we call it D, maybe it's like a pretty random name, but this data storage layer is sort of network attached disk. You might think like iSCSI or something like that. It doesn't have any logic in it. It just has like a bunch of disks that supply with storage for your data, but they are pretty dumb, and all the logic is in the system itself. So they don't do write, for instance, because write is in this software-driven layer. And all data ops are separated from the curators. So you have the control plane, which is curators, and you have the data plane, which is D. And then your client will interact solely with D, moving the data, and like data location is going to be cached in your client library based on the query you did to the curators. Then there are silent curators, which are called custodians, which are not visible to clients, but do all the housekeeping, like fixing, for instance, in situation where the disk fails, then they will be like making sure that this write, like virtual write operation actually works. So we'll find some D storage for your data, and we'll move it in the background, and we'll also make sure that, for instance, no leftover files are there, etc. So this is like an important duty. Stuff disappearing. Okay, so how does the typical cluster look like? So imagine you're YouTube and you want to serve a lot of data. Then you're going to interact with the Colossus control plane. Also GCE VMs, like Google Cloud Engine VMs, through GCS control stack are going to be interacting with the same Colossus control plane, and also like our internal ads pipeline is going to be interacting with the same Colossus control plane, and they are going to have like unified abstract request. I want that much storage, and I want that storage to be that resilient against failure, and I want that storage to be encoded in that particular way, and this is all, and please supply me with that storage. Right? And then the Colossus would be responsible for giving you this storage. And of course, this is like kind of difficult, because there's like a lot of diversity in hardware. So, you know, we have spinning disk, we have flash, and we are buying the disks that are available on the market. Like, you know, there are shortages on the market, so maybe some kind of disk that we would wish to buy is not available, but we can buy some different disks, and we put that into that storage. Then we have diverse requirements on the clients. So the clients, you know, have different expectations on data durability. Maybe something like it's a temporary data that you don't want to store too long. There are like varying erasure codes, so like this resiliency against failures, like how to make data withstand disk failures. Maybe some data is very, very important. Maybe some data is not so important. So like if it fails, you can reconstruct it. So like this is just a cost trade-off. And I/O prioritizations, like the performance of data like you would like to get. Then there's like fault tolerance, intelligent management of disk pool, and transparent recovery from failures. That's, as I said, that's like on custodians. And then we have virtualized resources. So, you know, like in the end, you just want to have a lot of bytes, and you want to have a lot of I/O operations. And you specify how many, and then like the system will supply you with that. And this is, I think, the biggest advantage, because you don't, as a client, you completely don't need to think about like how many disks, what shape of disks, like how to make a write, like which level of write, etc. It's like purely declarative storage, and this is like biggest advantage of this model. Okay, so let me just walk you through like one use case in detail. This is mixing flash and disks. So, you have some hot data that you refer to very frequently, and then you have some cold data, which is like maybe some data you very rarely revisit, or might even not visit at all, like logs, for instance, or maybe some sort of other data storage. Then the hot data should be available very quickly, and the cold data should just have the space to be stored. And like typical disks come in different shapes, so you might have a small disk, or you might have an SSD disk, which is like a lot of hot space that you can supply with I/O, and then you have a big disk like 10 terabyte disk that will probably just be good as a cold storage, or maybe even tape. Like tape is very, very cold storage. So you'd like to automatically balance that data, and this is the job of Colossus. So Colossus just figures out like what is your usage pattern, and like in the background it will pump your data from that disk. So if you like start pushing a lot of cold data, it will find some disk with a lot of storage space, and then that data will be pushed to there. And this is like the image, the typical image when stuff works well. You see the colors, like red is serving hot data, blue is just serving cold data, and like gray ones are like, I don't know, something failed. So this is like a typical monitoring image of a healthy cluster, and like in each box is a D server that is something that contains your disks. And this is essentially like the shape of our storage, and like this is how the storage works. And now we can move to some practical application of that, and this is also what the team I'm member of works on, and Sławek will fill you in with details of what we do.
Yep. So Janek told you a lot about, you could say, low-level storage, how it works in a single cluster, in a single data center. But we actually move a lot of data. So you can look at the Google as a gigantic distributed system, where you have dozens of clusters which are interconnected, and data that flows between these. And first question is, why? Why do we need to copy that much data? Why do we need to move it all the time? Well, actually, there's a lot of good reasons to move data. One is that you want to have your data closest to your customer to minimize the latency. And it is quite often that we will generate data in a single place, like the index for search. That's a very expensive thing to calculate. So we will not calculate it in every cluster because that doesn't make sense. We'll calculate it in one place and then copy it everywhere. But it's a big thing, not only expensive to calculate. So we need to move it in a reasonable manner. We, of course, also replicate just for durability. Not only single disks fail, as Monica mentioned, whole clusters also fail. We do really our best to prevent this from happening, but disasters do happen, natural, and we need to be able to move data to ensure reliability. We also turn up and turn down clusters. This is a very dynamic landscape, and whenever you turn down cluster, well, you need to move the data out. We also have a lot of workloads which really don't care where they run. A lot of the ML stuff doesn't really care if it runs in US or in Europe or in Asia. What it cares about is that you use cheapest possible compute. So we move a lot of data to chase cheap compute, the places where we actually don't need compute and we have spare capacity. It also generates very big data moves. Also, after outages and restoring backups, we also need to move data from other places. So how hard can it be? Like, it's just copying data. Everybody does that every day. It needs to be easy. So it turns out it's quite hard. And the main reason it's hard is that there is a lot of data. And when I say a lot, I mean terabytes or dozens of terabytes per second. So if you do kind of a back-of-envelope calculation, assume gigabit Ethernet, you need 10,000 of these gigabit Ethernet cards to have 1 terabyte per second on the source side. You need another 10,000 on the destination side. So even that makes things hard. You need 20,000 entities to move the data, at least. And you probably cannot saturate the gigabit Ethernet, so you actually need more. So orchestrating that is hard, even if you take everything out of the picture. But the orchestrating of all these machines is actually not the hard part. But like, all the resources that we use are differently available in time. So you need to read the data at the source. You need to move it through network. You need to write the data at the destination. You need to encrypt it on the flight, checksum, do stuff. So you also need compute. So you actually have all of these resources which vary with availability in time, and you need to orchestrate it so you don't actually waste any of these. So if you can read, you do read, but if you can't write it on the other side, it doesn't make sense to do the reads. So there is a lot of complexity in how do you orchestrate this whole picture. And to make things harder, you don't have a single point where you know the whole picture. Because, of course, when you move from East US to West US some data, you don't want a random failure in Europe to impact this move. So you actually do not have an overview of what's going on in your system. You need an algorithm that works in a distributed way and emerges or like converges to a good enough solution. And that's what we to a large extent do. It's not perfect, but it is very resilient. Yeah, and to add to complicated use cases, one of the initial reasons our copy service was created is actually something like a web search index. You create it in one place, then you want it everywhere. So you create it in cluster A, and then you want to copy it all over the world. So what do? Well, you do that. It's simple. But actually, it's not, because it turns out that copying through transoceanic links is way more expensive than copying within a continent. And that is way more expensive than copying within a metro or a zone. Because transoceanic links are congested, they are expensive to build, so we really, really want to move the data through these very expensive links as little as possible. So what we do? Well, we do an optimization. We try to build as full picture of the whole thing as possible. Again, as I said earlier, because of isolating failure domains, it's not always possible to have a full view, but we try to have as good a view of the thing as possible. We'll know what are we copying currently. We'll have some previous copies that we did, so we know that, okay, we saw that file earlier, we copied it already into a few places, so maybe we can use one of these as source rather than the one that user provided us. And we also will consult the networking layer, asking it basically how expensive is it to copy bytes through this specific link. We'll calculate a minimum spanning tree over that, and basically that will define how we want to copy things. So you can end up with something like this rather than the first picture. But this again introduces interesting questions and interesting problems, because what happens if the copy from A to G is not progressing? It may fail for multiple reasons. One of them may be that, for instance, you don't have write capacity in G. Well, then your copies to F and E are now stalling. But why? Like, a user who said they want to copy from A to E doesn't really care about their copy from A to G. So why their copy from A to E is stalling? Well, technically it's stalling because we've serialized the copies. So now we need an ability to detect this and fall back to different routes based on the performance of the copies we're waiting for. Which all makes things complicated. And we to a large extent solve it through this not that hard to understand or not that hard to devise architecture. We actually have few components. One which understands and drives the whole copy and this will always live in the place where the original file lives. That gives us the best overview with fairly good resilience to failures in other clusters. What we'll also do, and what is a very interesting property of our system, is that, as Jan described, the files are stored in this very parallel file system, which for a lot of intents and purposes can be looked as a system where you can get infinite throughput as long as you're able to drive it. As long as you're able to read files, you can get infinite throughput because you can read every part of the file at the same time. Which means that our system, if resources allow, will basically copy any file in constant time, regardless of how big it is. Because we will split the file into millions of elements and then copy all of them at once, if the resources allow. So of course you need something that will orchestrate that, and then you need something that will manage the resources on both sides. So that will figure out, can I read fast enough? Can I write fast enough? Do I have network between source and destination to push all these bytes? Do I have actual compute power to be able to do all the hashing, all the encryption, and all the stuff that I need to do? And we actually do these independently in source and destination. This again gives us better resiliency, but also means that figuring out if you have both source and destination is kind of hard. And because we have dozens of these clusters, if you would like to centralize this, you get a massive spaghetti of dependencies. So we will independently manage source resources, destination resources, and whenever this whole line is put together, any one of these components can basically veto a transfer, saying, I don't have resources, I don't have network, I don't have read capacity, I don't have write capacity. What is interesting, some of these components actually handle a lot of RPCs, and a lot is millions in parallel. So it's super interesting to see the virtual threads. That's something that could possibly push us from the async world to sync world, which is very, very enticing, because async is damn hard. And that moves me to one of our realizations. Our system is built in a very, very asynchronous way. We will run millions of parallel RPCs per a single server. And generally, you cannot run these synchronously. Like, you cannot have millions of threads. That's just not feasible. Or was not feasible until recently. And still is for us, because we've built it in C++. And that means that the code is very, very hard to understand because of all the asynchronicity. We basically have all the problems described yesterday with async code, callback hell, really, really complicated flows where you look at the code, you have no idea what's the causality of things. So definitely more modern approaches and more modern languages are very interesting. This is a fairly old system, so a long time ago, C++ seemed like a very natural choice. It would still probably be natural choice for the data plane because you have so much servers there that you really want to squeeze every last possible bit and every last possible CPU cycle that you can. But for the control plane, there's a lot of stuff going on there, but it's really not that expensive from a resource point of view. So we would happily trade some performance for velocity in development. So that is definitely like the things we see here are very, very interesting. Yeah, so what are our learnings from working with such a system which has this high parallels and large number of servers? So one thing is that with millions of servers, you will get every possible thread interleave that you can figure out. Like everything will happen, both on the single server level and on interacting between multiple servers. So if you have a race condition, it will blow up. That has its upsides and its downsides. The downside is obviously that you need to be very, very careful. The upside is that if you have things failing, they'll not be failing once a month or once a quarter. They'll be failing every minute or every second. Which means like debugging is challenging, but you get a lot of data to debug from. So that's nice. And of course, sanitizers, that's a must-have, at least in C++, using thread sanitizers and address sanitizers, which will catch majority of potential data races and undefined behaviors. That is very, very helpful. Probably most of you are not dealing with undefined behaviors on a daily basis. Trust me, that's not the nice part of C++ experience. Yeah, like there is, again, the things do fail. They do fail all the time. So in this kind of scale, you cannot monitor for errors because errors will happen all the time. Even if your code is perfect, everything runs, every corner case accounted for, you can get bit flips. And I always thought like bit flips, that doesn't really happen. It's just like, it's just some academic thing. So we run ECC memories in our data centers. So we can correct single bit flips and detect double bit flips. We know that these happen because we monitor that. We know how many of single and double bit flips happen. From that, we can calculate how many 3-bit flips happen. These are not caught by ECC checks. But we know they do happen because the probabilities are big enough that we know that they will happen. So it's perfectly plausible that you read data, send it, and get something else. It's plausible that you read data and calculate a checksum, and you've actually calculated a checksum of something else because there was a bit flip. So you need to be very, very resilient. You need to check things again and again and again, and layers of security, layers of checks, because every single one of these layers not only can, but will fail at some point. So that's why we calculate checksums multiple times on multiple layers. D calculates checksums, then Colossus calculates checksums, then we calculate checksums, then networking calculates checksums. A lot of checksumming, a lot of CPU cycles going into checking things that seemingly you could skip, because why would you checksum the same thing 10 times? But then it turns out that in our fleet, we have a handful every month of a checksum that's calculated at the end of the things and should never, ever fail. Like, there is no plausible reason for it to not match. Still doesn't match. So, like, it's you need all these layers of security to be sure that your system actually works. And probably if you work on way smaller scale, the probability of these happening is very, very low, so you can just live with it. But when you copy exabytes of data every day, these risks stop becoming acceptable because you know they'll happen. Yeah, so in conclusion, I hope I hope it was interesting for you, even if not very Java-centric or JVM-centric. I hope we showed you both in the cluster and between clusters what we do, like how Google Storage works on a very high level, and also on some lower level, and some tricks we do with SSDs, tricks we do with copying data, and things like that. Cool. And I think we can move to questions. Hopefully we can do that or not. I'm sure we'll figure it out or not. Do you have a... Let's see.
Up. Here, yes. Okay, awesome.
Yeah, slides are great. Okay, and I think it should work, hopefully. Okay, let me see.
Let's click at
here. And yeah. I lost Wi-Fi. Yep. Hopefully it will go.
Let's give it like.
So maybe plug it in also from the top.
All right.
Okay, it's loading.
Loading. So maybe let's give it a minute because I think it's.
Or not.
No.
I don't know. Like it's loading, but not very quickly. Yeah, maybe let's start reading from the.
Okay, so I'll do. All right. So the first question is GCP Java API seems developed in rush and not ready. Also, documentation is messy and hard to find. Is it safe to use, or by default we should use the REST API? Okay.
Okay, it worked.
Okay, so we had it. Like, yeah, I already clicked it. I think we don't. I mean, we don't work in GCP, so I don't know like what is our visibility, and I don't feel like competent to comment on the GCP Java API. For sure. There's a process of commenting on the documentation or reaching out regarding the documentation. I mean, the GCP part is like welcoming every feedback about the documentation. And having worked in GCP, I know that the teams really value the feedback, and you know, it's like maybe it's worth reaching out again and again and making that point. So, I mean. That's all I can say, I think.
And answering the question, is it safe to use? I think it's safe to use in the sense that also in GCP we are making a contract for API. So for instance, it will not change immediately without any notification. So even if they're not perfect, I think, like as Janek said, we can improve documentation. We are like looking forward for the feedback, and we also do some promises. So we'll be supporting these APIs.
Bitflip statistics, yeah, I think not something that I can divulge, and yeah, it's not something that we publish. So sorry. Just like the teaser is that they do happen on a regular basis.
Can you share any interesting failures, outages that impacted the Colossus or any other Google storage services? Are there any public post-mortem documents? Yes, post-mortems that impact GCP are public. So if there is anything in Colossus that has happened and that has caused like publicly visible outage, it's like not of say internal infrastructure, but that that you know percolated to the customers, then for sure you'll be able to read post-mortem and learn from it what has been wrong, right? And having said that, I mean there is like this resiliency and layering in Colossus in every system. So we do a lot to stop the failure at the firewalls, like at the boundaries. So this is really, I mean, that's really hard for a failure to really propagate and start impacting customers. So, like, I personally, I don't know, but I don't have any like personal valuable stories that I could share about failures. Yeah.
Yeah. Maybe answering quickly the last one. Yes, always. Yes, we are. And BitTorrent, that's an interesting question. We actually had BitTorrent implementation inside. So BitTorrent actually solves slightly different problem. It's geared towards discovering sources in a very distributed, very dynamic system rather than maximizing throughput. we generally know the network, in the sense we know where the files are. So the whole discovery part of BitTorrent doesn't provide a lot of value for us. So in other words, because we know where the files are copied, we can make better choices on how to copy them and how to parallelize things while we are copying. There are also, BitTorrent is fairly hard to control, or it's fairly hard to make good promises on when things will finish. And that's a big thing for our customers, where they want to know how long it will take to copy. But yes, we had an internal implementation of BitTorrent that was used for some time. So it definitely makes sense. No same files are not shared between users, at least not at the storage layer. Potentially, some applications may implement that. Honestly, I don't know if anybody does that. But on storage layer, there are not. We have strict isolation between users. It's very risky to share stuff between users. So
I think it also ties into like the design of the system. So to have a scalable system, you have to have like this shared nothing, and it like the true cloud native thing, it just goes into your API and goes into your system design. So you cannot like plug the cloud as an afterthought. If you want to build like a global system, you need to make trade-offs also in the architecture of the system.
And files are identified with IDs.
Yes.
Like so numbers. And also an interesting property of our storage systems is that they are generally append-only. So you generally cannot mutate files. You can only append to them. So it's a fairly easy identification story, because like you know when you append to files, we know when you change them. And so like as long as you appended something, it's definitely not the file it was before, because you've appended something.
Rust. Yes, we would love to use Rust. In the past I did a lot of Rust programming. We have Rust internally at Google, for instance, in Fuchsia operating system. But I think the major problem with Rust is that Rust has a poor interop with C++. And we have a lot of C++ code base already there. So that is, I think, the main barrier to adopting Rust. But yes, Rust would solve a lot of problems that are inherent in C++.
Anybody knows something about Google Photos mangling photos?
Yes, I think there should be a public postmortem on that. As far as I know, yes.
Okay. Services developed internally. So a lot of services internally use basically the same storage technology as GCS, but they do interact via different API. So the internal products like Photos or Drive will not interact through the GCP API, but they'll use vast majority of the stack like vast majority of the same stack that GCS uses. Yeah, hope that. I don't know if it's mainly about the API or the internals. Do you use ECC everywhere? Everywhere is a very big quantifier, so probably not everywhere, but in most DCs. Like we have a lot of types of data centers and points of presence and things, so I don't want to say everywhere, because there probably are some types that we don't, but in the normal data centers we do.
How do you prevent hotspotting?
That's a very interesting question. So D stores very small parts of a file. So when you, okay, there are a few layers. First of all, when you have a file, we'll chop it up into very small parts. Like very small is like 4 or 8 megabytes. And every one of these has, gets a random allocated D server with some caveats on the randomness. So if you're reading a file, you will hit a lot of servers. So that prevents these servers from hotspotting because you read a file again and again. Then if you read a specific part a lot, that will probably require some more thought from the developers. But whenever you create a file in Colossus, you can define how it should be stored physically. One of options is that it's replicated, and you can say how much replicated it is. So in extreme cases, we see files that are replicated 100 times. So you will basically have 100 replicas of the same file, or 100 replicas of every part of the same file. So then you will just read from random one of these. So that, again, limits the hotspotting.
Yes, maybe I also wanted to say that, that there's some magic, as I already said, like this is all software-defined something, and we have also software-defined networking that has been discussed at other conferences. There are good papers about it, like Jupyter Rising, about our backbone. So we can allow the data be distributed across computers and at the same time accessible as if it was local or even faster to a computer.
Whoa, sorry. That was bad. Okay, we are back. Sorry for that. Oh, that's a good question. Higher than it is now.
But then you get a lot of, as a customer, you get a lot of goodness that we work on. So I think it would be fair to say that, that the way you sponsor the salary of all the programmers that work hard on giving you resilient cloud.
Yeah. What's our right amplification? That's a nice question. The answer, as often, is it depends. So for colder data, it will most likely be below 2. With all the erasure codes, and at least if it's a system that stores massive amounts of data, where the write amplification is really something that we want to limit, it will be below 2, although there will be over 2 durability factor because of the erasure codes we use. For hot data, it's way harder to answer because it boils down to how hot. It can be 100 in very extreme cases where the data is very, very, very hot. Most of the time it will be between 2 and 3. Like that's the standard amplification rate within a cluster. Within a single cluster it will be between 2 and 3, normally.
I think that covers also the next question. Yes, data is sharded.
Yes, data is sharded between multiple D servers. Also for durability purposes, like as Monica mentioned, disks fail all the time. So like you need things to be replicated to ensure that you don't lose data.
The whole storage cluster fails. Honestly, I've never heard about like the utter failure, in which like the cluster would fail with everything inside it. I mean, there are people in operations like who work on ensuring that there's some answer to every failure. So if the link fails, then for sure we try to find another way of connecting and
yeah, I think there are some. I don't know how much of it's public, but generally, like cluster-wide failures are very, 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 very rare. So it is a big event. It's not something like, while disk failures or rack failures or even the whole electrical thing that powers a row of rack failures, these are, you could say, common-ish, and they'll be to large extent for most of the developers fully transparent. Like nobody knows on the application layer that a disk failed, but even if a whole machine fails, like nobody notices that. But a whole cluster failure is an emergency, and it will take time from people to figure out a way out of it. While most of the data from while the data from cloud customers, especially the one that is in GCS, this is always replicated between clusters, so this will fall over transparently for you. Underneath, we will ensure that the replication factors are still true, so it will take some fixing.
Okay, I think last question. Content check. In the database, while replication, do you check the millions, billions records? I think yes.
I think the answer again depends. So a lot of replication is thus done on a different logical layer. So we don't replicate. Like Spanner is kind of specific, but a lot of replication is not done on a database row level. It's done on level of files, write-ahead logs, and things that for the replication systems are just a bunch of bytes. So you will check some bytes now rather than rows. As I said, Spanner, a bit different. There is a lot of replication on transaction level in Spanner. Well, again, like Spanner has different layers of replication. It will both replicate transactions within a group, and then it will do backups and replication on files level where it doesn't check single rows. Yeah, thank you. It was great having you, and thanks for a lot of interesting questions.
Yeah, I think we are at time, so thank you.
And yeah, just touching maybe on electricity, a lot of work actually now being done on reducing the footprint in Europe because of rising prices, but also because of the strain on the grid. So we are actually moving a lot of our workflows out of Europe to ease up on the grid and use less electricity here where it's most needed.
Right. Thank you.